All right, the final part of chapter 19, and mostly I would encourage working through a lot of the examples and the practice problems along with the author where you can. But I'm going to make a few comments about transmission parameters, which is yet another variation of the parameter types. We called impedance, admittance, hybrid, and all we did was vary the combination of driving variables against the independent variables. So let's go ahead with this, and we've got our usual network, 2 ports, okay? And we talked about voltage as a function of current, current as a function of voltage, voltage in as a function of current out, current in as a function of voltage out, those combinations so far. Well, transmission parameters are yet another one of those, and let's just look at this. Here's the basic idea that's important. You've got what? This is all an input side thing going on here, right? This is input. And the dependent, or the variables over here, I'm not going to call them dependent. This is output. Okay? So what you have here is in as a function of out. The input variables are the input value variables, are a function of the output variables. Okay? And these are one form of the transmission variables, and we just call them A, B, C, and D. Okay, and notice now we've introduced minus terms here. Okay, since it's C times the voltage out minus D times the current at the output. Okay, so this would be like if you drew a voltage in a little loop here, you'd have plus V2 or something times V2 minus something times I2 to close that loop there, and that's going to be create some activity back at the input side. Okay, so we write it like this, and in matrix form, right? This is the tight form of this, and we're going to call this little package right here T, right? That's a transmission variable, the transmission parameters. Okay. Now, what are they? Well, we know because we're now so familiar with this form going on here that A, to solve for A, it's going to be a function of what? V1 over V2 when this term is 0. Right? This is what we've always been doing. Right? When we want to evaluate one of these parameters, to evaluate the parameter, a parameter, we set one of the independent terms, I'll call it the right-hand side, equal to 0, and solve for the remaining term. Okay, so what is going on? How do we set the second term in each of these to 0? By setting I2 equal to 0. We set I2 equal to 0, right here and here. So this means it's going to be an open circuit. All right. When we want to solve for the second part, we need to set the first part to 0. So we get rid of the V2 terms by doing what? This is going to be a short. Same as we've been doing all along. Okay, it's just the definition of some conditions to create some terms. Only now, instead of having a term on the left and a term on the right be over here, we've got basically in and out. Okay, so this is the first time we're seeing that clear description of input versus output. Okay, and I think there's more than one way to do that. You can have output versus input, and notice we've used the nomenclature is the same terms here, except they go to the lowercase, right? And you still end up with a t variable. Okay, so the t variables, now we just need a new name. We had z, we had y, we had h. Okay, but now we just pick the letter t because this relates to transmission. Something's moving, some signal is moving left to right here. Some signal is trying to move through this device. We're transmitting it from the left side to the right side. Okay, so that's important, and you end up with similar parameters, only now what are you doing down here? Now you're you want the input side current to be 0, so again that's an open, and this, to get the voltage on the input to be 0, is going to be the short circuit condition. Okay, now, by the way, before I leave this, you notice the terms open and short are chosen because that's literally what you're doing. If you want to find these parameters over here, B and D, right, and they are functions of a short circuit, you literally come here and can attach a wire on a circuit and then take your measurements. Take the measurements for I1 and I2 and for V1 and I2. Okay, so in all cases, not just the transmission parameters, the parameters can be found in the lab. Using test conditions. Okay? So all of these parameters that we've found are laboratory attainable. They're measurable. So when you think of transmission parameters and you think of a transmission wire that's stretched for miles, you're thinking, oh, am I going to find out what the problem is? This is awful. It's not awful. You can have a short circuit applied at the output and take some measurements at the output and the input. And you can find faults. You can find, so the transmission line, system, whatever, can be characterized ahead of time in a known good state, and then it can be tested later to get clues and pointers to where the faults are. Okay? Okay, so now I'm going to talk very, very briefly, mostly just to indicate a few things. You really need to work a lot of problems, and I'm not going to belabor that in videos because there are excellent problems in the text. But we're going to interconnect two networks, and there's going to be three ways we do this. We can hook them together in series, just like we would hook together, you know, a couple of series resistors, right? You know how that would be, right? You'd hook them up in series resistors. Okay, well, we're going to hook them up in series. Then we can hook them up in parallel, right? So we can hook up networks that way. And then because we have, but these are not two-port devices, right? These are one-port devices. There's two terminals, and there's two terminals. With two-port networks, you can hook them up in series and parallel. The parallel you can kind of visualize, right? Here's an input, here's an input, there and there. The series, which we're going to do first, is a little awkward looking. But then we can just simply cascade them. So let's start with serial. And again, I'm mostly going to just point some things out for your awareness. So look here. This is, how do you get serial out of two-port networks? I mean, what you want to end up with in the end, right, is this. This has to be, you have to end up with a two-port network in the end. However you hook these together, if you end up with anything other than a two-port network, you haven't connected things correctly. So I need to end up with a two-port network. Here's V1 and I1. And notice the I1 just goes around like this. Well, actually, I probably should have drawn the box over here, because this is what it is. And the same thing with this. This is I2 over here, right? So somehow that's your resulting two-port network. So what happens inside? The way those have to be interconnected, you've got current coming in, right? And then, so you have current coming in, 1 and 2, and those are the same. The important thing is that the voltages across the sum of the networks adds. So back to this little picture here, if I wanted to say those are in series, I add, V1 and V2, right? Those add. So the total voltage is the sum of those two, right? The total input voltage here, V1, has to be the sum of the first terminal and the second terminal, right? The second pair. So that forces this connection. That's what defines it as a series connection. Okay, the drawing looks weird. I'm not sure there's a great drawing that would be better. The same is true of the output. You have to connect the output terminals in series. Okay, if I drew this a bit at a time, individually, I would simply be connecting output terminals. You really have to view it like that. Oh boy, where I've got input current and output current, and the voltages sum. So here's the sum of the voltages and the sum of the currents. To think of that as series is kind of weird, because you've got input voltages summing and output voltages summing. So, but it is a definition then of series, and the mathematics of that is going to be on the input side, right, and output side of the upper terminal, right there, 1A and 2A, right? I've got those voltages. So this is the description of NA, right? This is network A up there, all right? I'm going to have a similar one for network B, okay? And now I'm going to do my math, the straightforward and simple math around this. The voltage, the new voltage number 1, right, this guy, is the sum of those two voltages. So there it is. And the same is true for V2. It's the sum of those voltages. So now if we expand that, what is that? Well, we know that V1A is this, and V1B is this, Okay, and we can do the same with 2A and 2B. All right, so it's just simply plodding through the math for the kind of hookup that it is. We did this same thing back in the very beginning when we had Kirchhoff's laws and we were doing nodal equations and loop equations and stuff. We're doing the simple version of the same thing here. So once we have this, we recognize here's an impedance matrix and here's the various parts of it. There's one part, there's another part, right? We just got these from right here. We just got this from right here. Okay? So in the end, what does that look like? Some large scale, some master Z looks like the sum of the individual Z components. Notice the 1, 1 and 1, 1, 1, 2 and 1, 2. It's not 1, 1 connecting with 2, 1 or anything like that. It's just straightforward. That's the series activity, and this is series notation. Right? The sum of impedances is what you do in series. Okay, let's take a look at putting a couple of networks in parallel. Now that we're sort of in our head grounded here with the series idea, and we sort of know what to expect, right? We're thinking, oh boy, parallel impedances, we got that product over the sum. This is going to get really bad. But remember, parallel admittances are just the sum of the admittances. So let's think about how we really want to do this. It's easy to see here that they're in parallel. Here, this point is connected directly to the input of both of those, and likewise for the negative terminal. So now both networks receive the same voltage, right? V1 is the same on both of them. In the last case, I1 was the same, right? The current was the same. Here the voltage is the same, and the same is true on the output. The voltage is the same. So let's look at the resulting equations for that. Now we're using admittance parameters, right? The current, the I1 current, and the I2 current on the A network is admittance times V1A plus admittance times V2A, right? All we did was just break down into an A network and a B network. Okay, so we kind of anticipate where all this is heading. The pattern's going to look just like the other. What? The total current, the I1 current. Now the current out here, right, is going to be the sum of I1A and I1B. So here's I1A, Y11A, V1. So there's that plus that. Y12A and V2. Okay, so those four terms make up, right, these four terms come together and they make up I1A, right? Likewise, the other four terms are going to come together. What did I put? Well, it's not four terms, it's two, I1 times V1. And these other two are going to come together and they make up I1B. And we don't want this in there. That's just the combination. That makes IB, I1B, right? So we know what we're headed toward here. We're headed toward an I1, right? An I1 is equal to I1A plus I1B, right? And we can keep on going with a lot of this so that we get I2 is equal to I1 2A plus I 2B. All right. But we end up with just another set of matrices. All right. And the reduction of all of that is going to be exactly parallel to the impedance. I'm not going to repeat all those steps, right? Because I'm showing the key of it here. There's I1A, I1B, 2A and 2B. But then it's nicely factored right here, right? This combination and this combination, they just turn out to be the sums. So that the total y is just the sum of the individual of the network y's. Okay? And you get there, you get immediately to it. So really, if you follow the impedance, the series one using the impedance, this one doing admittance is identical, except you're leveraging the fact that you're going to use admittances and not impedances, and you're going to end up with a sum of admittances. And you never get to that product over the sum of impedances business. Okay, so that's series, parallel. Series is a bit of a goofy one there, and then parallel we sort of catch you because they switch to admittance parameters. And now the one that is probably the most, I want to say, practical, because this is typically how networks are hooked up in cascade form, right? We call this cascade. And what's going on? It's like, this is like I have an input and an output, and I put it into another input and another output, right? This is the thing you see when you see wires connected all over the place, or transmission lines. You have two wires, going in somewhere, and something happens in network A. Then two wires go out. Like maybe this is an amplifier, maybe it's a filter, right? And then this is an amplifier, and these things get separated. You see this on a soundboard in production studios. This is basically what's happening. The stuff gets hooked together. So now, what about the mathematics of this? Well, we can go back and say, well, we did our impedance parameters, we did our admittance parameters, now we're doing transmission parameters. All right? So we're back here with our T parameters. Okay? Our T parameters. And and we're going to back to two networks, network A plus network B, right? So nothing's really changed here. The voltage at the input is the voltage, just this is our big deal network, right, that we're going to analyze. Right? That's the whole thing. And notice it also is a two-port network, right? If we wanted to draw it like Quickie, we could say, what do I want to end up with? A network here, which is network A cascaded into network B, and then output, right? And this is my in and this is my out. Right? Well, this box is this summation here, so this is the math of that. So V1 is V1A. That's no big deal. That's just a redefine. Okay? And the same thing is going to happen on the output. This is a define. I'm just saying this is my big time network, right? V2, V1, I1, I2. So there's that. But now we're going to find some in-between terms, because these are the terms that we have the math for, right? These are the terms that we've got over here, right? These terms and these terms. These are the terms that we've got over here. And again, here, and here, right? So here we've got what? In, out, in, out, all right, of each piece. And that's all that goes on. So you can now imagine I could iterate this many times and it would just be more and more the same. Well, the way I do that, this is the beauty of the matrix mathematics now. I don't have to go into huge detail. I can now treat, look, this actually even, where am I at? This actually even looks like network A and network B. Okay? And all this did was give me the confidence that I could write the total up here. I could write this as V1 I1 is equal to some A total, some C total, some B total, whoops, some D total, right? I know I'm headed for this, and I can write it with confidence. Let me finish here, right? I know I'm headed to this sort of thing because it's a T network. All I've shown now is, oh, to do all this, I can rewrite NA plus NB, whoops, down here, I can rewrite NA plus NB. The product of those two is just some new big matrix, which is the total. This is what I wrote as total up there. And lo and behold, that's just the product of transmission parameters directly. So what does this say? The nice thing is, if I'm cascading networks, which is an important thing to be doing, if I'm cascading networks, all I need to know is the transmission parameters of each network, multiply them together in matrix form, right? This is a matrix multiplication. Multiply them together in matrix form, and I get the matrix for a combined network. All right? And the other variations, again, as a reminder, for the series and the parallel, if I treat the series impedance parameters like series impedance, I get a new matrix of the combined network. If I treat the parallel admittance parameters as, and sum them, treat them as admittance parameters and sum them because they're in parallel, I have simple mathematics. I don't have to get into complex mathematics when I am combining networks in series, parallel, or in cascade. Okay? And I will conclude chapter 19 with this.